Hey, what's up, guys? This is Chung here. So today, let's take a look at this LeetCode problem here. Number 378. Uh, kth smallest element in a sorted matrix. Okay, given like a n by n 2D matrix, which each row and columns they're all sorted in ascending order. Basically, each row and column they're all sorted. So it asks you to find the kth smallest element in the matrix. And note that is the kth smallest element in the sorted order, not the kth distinct element. So what does this mean? It means that let's say we have a 1, 2, 3, 4, 4, 4, 5, and 6, and 7. Uh, so let's say if this is the sorted array, right? Basically, and if it asks us to find the let's say if the k is equal to 4, okay, in this case it's 1, 2, 3, 4. That's 4, right? Then the answer is 4. How about when the k is equal to 5? It's still 4, right? Because it's asks us to find the k smallest element. Okay, so k equals to 6, is also 4, and k is equal to 7, then it's 5. Okay, basically that's what this uh this sentence is telling us. Mm, cool. So, mm, what's the first solution, right? Since they are all sorted, okay, they're all sorted. I think the first approach will be try to maybe find the correct row, and then try to find the next element. But this is like a 2D array, right? And they're sorted on two directions, so that won't be that easy. I mean, a brute force way, right? What's the brute force way? Of course, the brute force way will be we need to sort. We need to sort the entire matrix, okay? And then we just find the case element. That's gonna be the brute force. But for that one, we have to basically uh, that's gonna be a n squared, right? Uh to sort like the n by n like matrix, the total elements is n squared. And to sort that, we're gonna have like n squared times uh, log n squared, right? That's gonna be the total time complexity, which will be a lot basically, right? We're gonna sort everything, and then we find the case element from it. Okay, that's the brute force way to sort element, but then we're not utilizing the case that each row and column they're all sorted. So what's what's a better way of sorting, right? To do the sorting. I mean, if you guys remember, how can you sort like two sorted lists? Let's say if you have like sorted list here, A here, and then another sorted list B. We have a 1, 2, 5, 7. Here we have a 3, 4, 6, 8. So how do we sort this two sorted list, right? We just have two pointers basically, right? We have two pointers here, and every time if this pointer has a smaller value than the other pointer, we okay, so this is the smallest number among those A and B, and then we will have like and then we move this pointer to the next one, okay, and then we keep comparing that. Whoever has a smaller number, that's the next smallest number, and then after that we move the pointer to the next one. So in our case, right, it actually since each column and each column and the rows, they're all sorted. Basically, it's just as if it's like we have unsorted list. Okay, either way, we can treat like the rows as a sorted list, or we can treat a column as a sorted list. It doesn't really matter. We can do it in either way. So now the problem comes down to I mean, we need to sort like unsorted list, and then and while doing the sorting, as you guys can see, right? So while we're doing the sortings, actually, after we after doing the case sortings, then or the minus one or the k minus one sorting, then the next result will be our sorry, the next smallest number will be our result, which is the kth smallest. So, and how do we sort unsorted list? It's a common way is using the priority queue. Okay. So how do we use the priority queue to sort this unsorted list? Let's say we have list A. Let's say we have C here, and we have D, and we have E. Okay. So the way we're doing the what the mm, the priority queue is that we we push we push each array's first element, okay, into the priority queue. We have a priority queue here, okay. So while we're pushing that, we also need to push not only the numbers, but we also need to push like the which uh, which array this number belongs to, right? So that when we pop that number out, we know who is going to be the next number of that number, right? So and basically we just use the priority queue to maintain the current smallest number. And after pushing each of the elements, uh, after pushing each list first element, then we just keep doing the heap pop. And every time when we do a heap pop, we know that's the current smallest number, right? And after popping that, we're gonna use the informations along with that number. Like in this case, it's gonna be uh, the identifier of which list that number belongs to, and then we're gonna move that the cursor or the pointer to the next one, and then we're gonna push that one back to the priority queue. And when we leave, we will need the priority queue to tell us after pushing this one who is gonna be our next smallest number. And we just keep doing that until we finish all until the priority queue is empty, right? Then we have a sorted list. But in this case, since we only need to sort k minus one times, we can simply store we can simply save some time. But that's basically the idea. And yeah, and when it comes to this problem, and how can we allow besides the number itself, how can we know like which list it belongs to, right? We just need to store the basically the current numbers, the coordinates that the row and column, and depends on if we treat the row as a sorted list or the column as a sorted list, we can just move that numbers either one to the right or one down. Okay. Cool. I think that's pretty much the basic idea of the first solutions. Let me try to implement that. Okay, so the first one is the length of the matrix. Okay, and let's see, and then we need the priority queue here. Okay. Okay, so that's a priority queue, and then like I said, let's push. uh, each of the elements, the first element into that is a priority queue. So in my case, I'm going to use like the column. I'm going to treat each column as a sorted list. Basically, so this is a sorted list. This is also a sorted list. This is also a sorted list. So that when I push the starting point, first element, I'm going to basically push the first row into the priority queue here. For J in the matrix, sorry, in range n here, and heap q dot heap push, okay, priority queue and matrix 0 dot j, okay. Yeah, like I said, we cannot simply push the number itself because later on when we pop these numbers, we need to know who is gonna be the next number of that one. So in order to get that one, we also need to store the index along with the number itself. Okay, so that's the index of the current number, and then we just need to do this sorting, right, or the heap pop k minus one time, so that the next one will be our case number, right? So that's why I'm doing a k greater than one to do a k minus one loop of this. So I'm gonna have a current number dot I dot j, right, equals to the heap q dot heap pop priority queue. Basically, every time, so now every time I have a heap pop here, this number will be the current smallest number, right? And okay, and then like we need to push heap q dot heap push the next number. But before doing the next numbers, we need to do like the check, right? Basically, if the current index has reached I mean if the current I current I, right, has reached the last row, basically that's the last element. We cannot there's no point of basically we cannot there's no more like next number to push into the queue. So that's why we have to do a simple check here. Basically, if the I is smaller than n minus one, okay, then we do a heap push here. Priority queue. So the number will be the matrix, okay, and the current I plus one dot j. So this means that let's say, for example, if we pop the one out, okay, if the current number is one and the index is zero and zero, so the next one basically we know this I minus one means that okay, since this I belongs to the j column, right? That's why we're only going down. This means we are always going down by one, which is the 10 in this case. Okay, and also the index along with the value. Okay, yeah, and of course we need to decrease the case by one. Cool. Yeah, so I mean after k minus one heap pop, so the case time will be the case smallest number, right? Which happens to be our answer, right? So we can simply return the priority queue dot zero. That will be our answer because this one will be the case smallest number, right? After the k minus one heap pop. Cool. I think that should work. Oops, oh, sorry. Yeah, since we're storing like a tuple here, it's the first element. Okay, cool. Yeah, see, it's pretty straightforward, right? Yeah, I think it's a beautiful solution. Basically, you just we just need to like utilize that sorted case case sorted list, unsorted list, and then while doing that sorts, it's easier. It's very easy to find the case smallest number. So and the time complexity for this, I mean, is the actually, you know, we can even do a small like improvement here because, you know, actually we don't need to push like all n elements into the into our heap queue here, right? Because whoever is smaller, it's fine. I think it's we can even do this, right? Because minus n and the k. Will also work. Let's say we have a huge n here. Let's say we have a huge list here. It's very big, but the k is like, let's say we have a hundred like by 100, but the k is like what? K is like 5. Okay, so in this case, we just need to push at most 5 rows. That's the most rows we need to be able to find the case smallest, right? It kind of makes sense. So let's try to run. I think it should work. Yeah, but even though I mean, it didn't change a lot, but this thing, I think it's because the test case, the k and n, they are pretty close. Okay, the k and n squared, I think they're pretty close. So yeah, basically the time complexity for this, what's the time complexity? So it's going to be whoever is smaller for this one, and the heap push is like O of k. You know what? Actually, let's assuming we use n here. Okay, let's make it easy. We just assuming we're using n here. So this one gonna be a n times log n, right? Yeah, to maintain like a heap. Yeah, plus what? Plus the this one. That's the k times log uh log n, I think. Assuming we're using n here, right? So that's gonna be n times log n plus k times log n, which will be the n plus k times log n. Okay, cool. So basically, that's our first solution here. But just by utilizing the priority queue to simulate the to sort unsorted list, and then we can easily find the case smallest number. And okay, and second, another solution is by using the binary search. Since they are all sorted, I think it's kind of like natural to try to think of like a binary search solutions. Yes, and it is true that this one can also be solved by the binary search. And let me try to write that function here, the solution here. Basically, for the binary search, since like I said, this matrix is sorted in two directions. So we cannot simply use the index binary search or the bisect, right, to find the element. Okay, so which means we have to using like the a helper functions to do it. And to search the answer, so again, the left will be what? Will be the matrix, will be the first one. So we need to have a range first. Matrix. So the left will be the first one. Okay, that's going to be the 0, 0. Okay, and the upper bound is what? Is the n minus 1 and n minus 1, because the top left corner one is the smallest and the bottom right corner is the biggest. That's our like search range here, because the case smallest number has to be between those two numbers. Okay, and then the template here, basically the left is smaller than right, and then we have a middle left equals to left plus right minus left divided by 2. So now we're gonna have like helper functions here, right? And I think one of the tricky part, it's not like tricky, but one of the things is kind of a little bit confusing is the when we do the middle here, right? So the middle could not may not be in the matrix, okay? So then if the middle is not in the matrix, right? How can we make sure? How can we make sure the ones we find is one of the answers here? Uh, that's because uh, it it because our helper function here that will guarantee that we will the final answer is has to be one of the numbers in here. So basically, the helper functions we're gonna define here, we're gonna count less or equal numbers with the middle. Okay, and I think I'm going to try to implement this one real quick. I think for this one it's not that hard to implement this, right? And then for j in range n here, okay? Basically, if the matrix I and j is equal smaller than the middle, right? We just simply increase the count. Else we can just break here, okay? And then we simply return the count here. I mean, we can also like break earlier, like I mean here, right? I mean if the matrix dot zero j uh, I sorry I0 is greater is greater than the middle, right? Then we can simply break here, okay? Because they're also they're both sorted in two directions. I mean, this is like optional, but it doesn't affect a lot, but it's simply a discount, right? And the tricky part is, let's say, so while we are like counts the equal here, it's because if we have 1, 2, 3, 4, 4, 4, 5, okay? Uh, yeah, and let's say the k equals to 5, okay? And when the middle is 4, okay? So when the middle is 4, and when we count 4 here, right? So we have like what's the count of 4 here? We have 1, 2, 3, 4, 5, 6. Basically, the count is equal to 6. Okay, and so when the count is equals to 6 and which is equal or greater than the k here, we know that okay, so this number, the middle, could be our one of our answer here. Okay, so like this. So basically, if the uh, count smaller or equal, less or equal. Okay, I use this less or equal. Okay, I'll do this. If it's smaller than k, if this one is smaller than k, then we know okay, it's definitely not one of our answer, right? Else we do a middle, sorry, we do a right equals to middle, and then we simply return the left. Basically, that's the idea here. That's the basic code here, So this one, every time when you have like a right equals to middle, this one is as if you're getting like the smallest number that's satisfying this condition. Okay, so which in our case that's happened to be our, I think that's exactly what we need here, because we need to find the case smallest number. So the case smallest number, it means that uh, whenever you have like a range of the four here, let's say for example, the so the four is in range what? One, two, three, four, four, five, six. So it means that the k, right? When the k is when the k is between 4 to 6, our answer is always 4, right? Yeah, so basically, this is as if like we're trying to find the smallest answer, sorry, the smallest number that, the smallest number whose the count the count less or equal to that number uh is equal or greater than k. Okay, and about how about the case, let's say the middle that does not exist in our array here. Let's say we for example this one, right? Let's say we have a 1, 5, 9, 10, 11, 13, 12, 13, 15. Let's say the middle is equal to 14. Okay, and so the count for 14 is what? It's 1, 2, 3, 4, 5, 6, 7. It's 8. Okay, it's 8. And okay, and our input, our case is also 8. Okay, cool. So our input is also 8. Okay, so which means, I mean, we're trying to find the smallest number, that satisfy uh this count is equal to 8, right? Then since 14 is not there, and who and since our count, is also is including the middle itself, so which means the 13, the 13th count will also be 8, right? Because 14 is not in our list, not in our like matrix. That's then it makes that the 13 always satisfy the count equals to 8. And since both 13 and 14 they're both satisfying our conditions here, that's why our answer is 13. So see, so this is exactly the purpose of doing the right equals to middle. Basically, we're trying to find the minimum number that satisfies this count here. So and this one plus the count less or equal plus the helper functions, that both of them are guaranteeing that our answer will always be the answers that will always be the number that is part of our matrix. Yeah, I think I haven't run the binary search code yet. Oops. Uh, okay, cool. So the test case passed. Submit. Cool. Yep. So it passed, right? So and yeah, I mean this binary search is a little bit like confusing, but still it's like a standard, like a little bit of variation, but it's not even a variation. The template are exactly the same, right? It's just that you have to think of like uh, with this template, how can you utilize how can you make the helper functions to help you navigate either to the left or to the right. And also why we're using like this the minimum answer template, right? Because I think that's because we are trying to find the we're trying to eliminate the candidates that does not exist in our matrix. Okay, that's why we're using like the minimum templates here. Uh, so for this like binary search one, I think so the time complexity for this is like the what? So here we have a uh, this one. I think that the range for this is like depends on the biggest number. So what's the biggest number here, right? That's gonna be our range. It's gonna be a log uh, a max number, right? A max number here times what? Times times the time we spent to do the search here. I mean, I think the search here is like, hmm. I mean, we can. It's possible that we'll stop early here. So I mean, the worst case scenario, this is like the n square, right? But since we're search, it's all sorted. I think, yeah, this one I'm not sure what's the time complexity for this doing the search here. Let's see. I think here is something like an n here. Yeah, it's close to n. Yeah, yeah, I would say it's like an n here. So here actually is the maximum. It's a log maximum minus minimum, right? That's the one. And here is the yeah, yeah, I would say it's close to n here because we have this like early terminations, and every time we search like n numbers, yeah, we search n numbers at most. That's why we have a n times log max uh, minus minimum here for the binary search. Yeah, cool, guys. I think that's yeah, that's I think pretty much for this problem. It's I think it's an interesting problem, especially I think for the first one. I think I highly recommend encourage you guys to understand at least the first solutions. You know, this is a very useful technique to not only solve this problem, but also like to basically to sort uh, unsorted list in general by using the priority queue. And regarding the second one, I mean, it's not the ideal case, ideal problem for the binary search. You know, it's we have a few like confusing point here. If you still don't quite understand it, it's fine. You know, because we have a way more other very good uh, binary search problems on LeetCode where you can practice. You can just maybe skip this one. Okay, cool guys. Thank you so much for watching the videos, guys, and stay tuned. See you guys soon. Bye bye.